Okay. As I told you last time, what is a solenoid? Once again, a reminder, what is a solenoid? We say a solenoid is the long copper wire turned in the form of coils like this, such that the diameter of each coil is much less than its length, the entire length. That means you have to make the coil of small diameter. There are two categories of solenoid. One is finitely long and the other one is infinitely. So you have only infinitely long solenoid in your syllabus. So you will be concentrating only on infinitely long. An infinitely long solenoid is a solenoid which has no magnetic field existing outside. There is no magnetic field outside the solenoid. Whereas magnetic field exists only inside. I will just draw a solenoid. How to make a solenoid? To make a solenoid, you will take a copper wire and just give a circular coil, turn it into coils. So to make a solenoid of the coils of equal size, we will be taking an insulated cylinder. Insulated cylinder will be like this. And on top of this, we will give turns like this. We are giving turnings on top of this. This thing you have done in class 10 also, but once again like this. Now the coils will be having then you have to pass current through it, then it behaves as a strong magnet. There will be electromagnetism and it behaves as a magnet. Now the solenoids outside the magnetic field is exactly zero. There is no magnetic field outside. Magnetic field exists only inside it, and the value is same. Everywhere the value will be the same. At the center also it will have same value. At the edge also it will have same value. Everywhere at all points it will have equal values. Current we are flowing I over here. Okay, now let us check the polarity and the direction of magnetic field. What direction does it have? Okay, a solenoid is made by taking a insulated cylindrical material, insulated cylinder, such as a plastic pipe we can take, such as a piece of paper we can take and fold it in the form of cylinder. And on top of it we will be giving turnings like this. Copper wire turning we will give and connecting it with a source, DC source. When we pass current I through it, then it will behave as a magnet. And a strong magnet it behaves as. As you know, there are so many circular coils. One circular coil produces pi times stronger magnetic field as compared to a straight wire. Last time I told you, I compared the two formulas and I told you that. So when you pass current I through it, it behaves as a strong magnet. Magnetic field outside the solenoid is exactly zero. There is no magnetic field outside. Magnetic field exists only inside the solenoid. That's what I given. Inside and infinitely long solenoid. And the value is uniform everywhere. Everywhere the value remains the same. Value of magnetic field at this point, at all points will be the same. And what is that value? We will find that. But before that, I will talk about the direction in which the magnetic field will act and what will the polarity of the ends. So here also we are using the same right hand thumb rule only we are using. So current you are giving this way like this. Current enters the circular coil in which direction, clockwise and anti-clockwise. We will see that the current enters in this way. It is entering from the inner side, not from the outer side. From the inner side it is being entered. The coils are given from inner side. The current will enter from the inner side like this way. When the current enters, in what direction does it enter like this? So this is clockwise. Sorry, this one is going like this. From the inner side, that means this end will behave as a south pole and the other end will be behaving as a north pole, because when the current is in clockwise direction, that end will behave as a south pole. This end will be the south pole and this end will be the north pole. You can try where this is the solenoid. Turns are given from back side. So back side, when you give the turns, what direction does it move in order to go to the other side? it goes in clockwise direction this way. The coils are given like this, so it is clockwise direction. Clockwise direction will make south pole and other end will be behaving as a north pole. Now the currents are flowing like this way. And magnetic field inside a magnet acts in the direction from south to the north. Magnetic field will be acting in the south to the north. This way it will act like this. And what is that value? That value we will find. Okay. So magnetic field inside, the diagram is this. The entire length of the solenoid will be taken as L. This entire length is L. Okay. And the number of turns given on the solenoid is N, capital N. Will be for anti-circuital law, we have to draw the magnetic lines of force. Magnetic lines of force, this will behave as a bar magnet. So bar magnet is a rectangular magnet like this. So the magnetic field lines will be coming in the form of a rectangle like this. This way you will draw like this. This is the magnetic field lines being created like this. A, B, C, D. I give the name here A, B, C, D in the form of rectangle. So how many lines are there? 4 lines. A, B line, B, C line, C, D line and D, A line. And we can do like this. Though it is imaginary lines, this is imaginary lines like this is running. Arrow can keep. Now we will be applying the Ampere circuital law. You can add now. By Ampere circuital law, we will be writing V dot dl equal to mu naught summation of sigma I. How many lines are there? This is called line integral. Line integral means for each line separately you have to do and add them up. How many lines are there? 4 lines. AB line, BC, CD and DA. So first line I write A to B line. This is AB. They are not the limit. They are not lower limit and upper limit. They are representing the line AB. Here I write B, DL, cos. Their dot product is cos angle. What is the angle between DA and B? DL is this length. This length and magnetic. This length is given like this. Between that length and this magnetic, how much is the angle? So 0 degree. I write 0 degree here. Plus next line is B to C. So write here B to C. Again write B DL. How much is the angle? Magnetic field lines, B is like this and A is given like this. How much is the angle between them? 90 degree. You can see that 90 degree. Plus next one is C to D. For C to D, this portion lies completely outside the solenoid. And we know the fact the magnetic field outside the solenoid is 0. So here I write B value 0. Outside is 0. I write 0 DL cos. How much will the angle? Angle will be 180. Though this does not matter because of 0 here. 0 into everything is 0. Last one is D to A. Back. D to A. Close line you have to take. D to A. There will be B DL. Again angle is cos 90. Is equal to mu naught. In one coil, the angle is I. Through the entire length, L, how much is the current flowing? Ni, because there are n terms given. Here I write Ni, total currents, summation of n. Sigma I values Ni. N times of each current, n times. Okay, now the next line. This will be 0 because of cos 90. Cos 90 makes everything 0. This thing will be also 0 because 0 multiplied by everything is 0. This will be also 0 because of 90 degree. Cos 90 degree is 0. Only this will be left over. The one which is going like this in the direction of A to B. That is south to the north direction. This only will be left over. So here we will be writing B. Integration DL will be becoming L. Integration of DL is L. Integration dx is X. So integration dl will be L. and that side we will be having only mu naught and I. Making B the subject of formula, B value will become mu naught n I by L. So this becomes the formula. Or this formula very often we write as B equal to mu small n I, where small n is n by L. This is called number of turns per unit length. Number of turns per unit length. This is the formula of magnetic field inside a solenoid. And what direction does it act? It acts in the direction south to the north, like A to B direction. That's what I showed there in the diagram. If you have the diagram, so this was the diagram. We were giving the terms like this. On the back side, the terms were given. This was south, this was north. AB direction was like this. So the magnetic field B value will be mu naught small n I, small n is n by L of this formula. But in what direction it will act? South to the north, this way. That's what I marked in the diagram also. And it comes along the A to B direction. A to B direction is like this. So that is the direction of magnetic field. That is the value mu naught n I. And polarity south and north we are determining by. We see the coil, what direction the current enters. Clockwise direction will make south pole, anti-clockwise direction will make north pole. So accordingly we are marking the direction as south and the north, and the direction will be like this. Main thing is the value of magnetic field, mu naught n I. So this is the formula of magnetic field of a solenoid. In class 10, if you remember, we used to remember like this, how to increase the magnetic strength of a solenoid. We used to say by increasing the number of turns, you can see over there, by increasing the number of turns, by increasing the current strength. Current value, when you increase, the value of magnetic field will also increase. And there is one more method, by inserting a ferromagnetic material such as iron, nickel, cobalt inside the solenoid. Inside this one, if we keep iron, soft iron, or maybe steel and all, if you keep inside, the magnetic strength will be increasing by a great value, by a great margin. That phenomenon is called ferromagnetism. So ferromagnetism we will be discussing in some other chapter. So just have an idea. So in classes we used to learn that. So this is the formula. This derivation is also important. It may carry 3 marks again. The 1 mark will be on the diagram, correct diagram. Second mark will be on writing this one, Ampere's law, and the third diagram on completing the formula, this equation, this one. Either this or this, any one. 3 marks question this is. Now, then the next application of Ampere's law is, though it is there in the syllabus, but it will not come. Next one, number 2 is, number 3 application is B means magnetic field at the center of a toroid. B at the center of a toroid. Okay, what is a toroid? I will tell you what is a toroid. A toroid is a solenoid in the form of a ring. If we have the solenoid in the form of a ring like this, round, or donut shape, donut shaped, donut. Have you seen the donut, the round one? That is called a toroid. So to make a toroid, we'll be having, if you are having this one solenoid, this solenoid you are having like this, and we are giving terms over here like this. This is normal solenoid. We had done just now. This thing only will be folding and turning it in the form of a ring like this. If you turn and take it in the form of a ring like this, it is a toroid. So from one end we will be giving the turnings like these turns. You have to give proper turns over it. Give as many turns as you can give. From one side will enter the current, from the other side will be taking out. This is the input, this is output. This is a toroid. This is called a toroid. It is a kind of solenoid, but a specific or a special type of solenoid in the form of a ring. Previous one we had only simply a solenoid that was in the form of a cylinder. That is called a normal solenoid, and this one is called toroid in the form of a ring. If you are having in the form of a ring, it is called toroid. We are finding the magnetic field at the center over here. Let us take the distance out here. This distance is A. This is the diameter of the toroid. Means average diameter from here the distance will be different. But this is the thickness is small out here. The diameter of each pipe is very small. So this will be taken as the average radius. So just now we derived right here for a solenoid. For a solenoid, what was the formula we derived just now? Mu naught N I by L. This was the formula we have already derived using Magnetism law. So we don't have to derive it again. We will be simply writing this one. Now next time we will be writing this B equal to mu naught N I. What is this length? The entire length of this solenoid. That previously was the entire length like this. Now the entire length is changed in the form of a circle or circumference. This L will be representing the circumference, the whole thing, length of the pipe. That pipe only we are rounding and making it in the form of a ring and making it a toroid. So this L is equal to circumference 2 pi radius. Radius is 2 pi radius. So this is the formula of a toroid. The two formulas are similar. In previous case we write only L, and in case of toroid, this L will become 2 pi. The rest of the thing remains the same. So we don't have to apply show the working how it comes again. This may, if by chance question comes, they will ask you write down the formula of magnetic field at the center of a toroid. So we just write down this formula. Or you may get 1 or 2 mark problem on it. Derivation, entire derivation will not come. It is connected to a solenoid. So this is the syllabus of according to the reduced syllabus of this chapter. Now we will be doing some problems of it. It used to be quite lengthy before, but now they have reduced it and now it has become quite small. So numericals. So you can write down all the formulas together from this chapter and then we will do. First formula is this one. B equal to mu naught N I by 2R. This is for a circle. This is at the center. At the center of circle. At the center of a circular coil. Circular coil. At the center of a circular coil. This is the formula. Second formula. If you have only one circle, the value of n is 1. If their circle is having 100 turns, then multiply by 100. If it is only one circle, you just have to not I by 2 directly. Second formula, B axial, on the axial point, the formula was like this: mu naught N I A square by 2 x square plus a square 3 by 2. This formula you have to see it lightly, okay? Don't take it seriously. This one, second one. Third one, B equal to mu naught I by 2 pi A for an infinitely long straight conductor. This only have in syllabus now, so this formula mu naught I by 2 pi A. And the fourth one is B is equal to mu naught N I by L for a solenoid, for a long solenoid or just for a solenoid. That's it. And if it is a toroid, only value of failure will change. The value of failure to 2 pi A. And that's it. These are the four formulas. On the basis of this, we will be doing the problems, and in some questions they may ask you mark direction, and also we will be marking direction using right hand thumb rule. If it is a circular coil, so again right hand thumb rule we will follow. Okay. Now some important problems, some important types we will do in this chapter. Remember, if it is a semicircle, the formula will become half of this. If it is a quarter circle, quadrant, 1/4 of this value. Accordingly, we can make modification according to the shape of the coil. Okay. Now, first question, first numericals. First problem. First problem is over here. Calculate the magnetic field. Calculate the magnetic field at the center of a circular coil. Calculate the magnetic field at the center of a circular coil. Circular coil of radius 7 centimeter. Of radius 7 centimeter. When a current of 2 ampere flows through it. When a current of 2 ampere. When a current of 2 ampere flows through it. Yeah, that is the question. So we do directly, we'll pick up the formula and do it. We have to find magnetic field at the center of a circular coil. Center. What is the formula at the center? B formula that is of a circular single coil. Mu naught I by 2R. We have to find the value of B. Mu naught value will put 4 pi in 10 to the power minus 7. The value of mu naught will be given in the last page of a question paper, and we are supposed to know the value also. Mu naught will put 4 pi into minus 7. I is current. What current is going? 2 amperes. Right? 2 into radius. Radius is given 7 centimeter. We are changing that into meter. 7 centimeter is 0.07 meter. And calculate the answer will come 1.8. 1.8 into 10 to the power minus 5 this time. That is answer. Now the second problem. This is done. Second question says, find the magnetic field. Find the magnetic field 1 centimeter away. Find the magnetic field 1 centimeter away from a long straight wire. From a long straight wire that carries the current of 1 ampere. That carries the current of 1 ampere. Long straight wire is mentioned. So we'll be following the formula of infinitely long straight conductor. What is that formula? B equal to mu naught I by 2 pi A. We use that formula. Put the value. Mu naught value is 4 pi into 10 to the power minus 7. I is current. Current is given how much ampere? We put that value 1 ampere. 2 pi keep as it is. A is a distance. Distance of the point from the wire is 1 centimeter. That means 0.01 meter. Now your answer will come 2 into 10 to the power of minus 5 this time. That's it. Question number 3. These are simple one. Question number 3 says, a circular coil of 20 turns. A circular coil of 20 turns and radius 10 centimeter. And radius 10 centimeter carries the current of 1 ampere. Carries the current of 1 ampere. What is the magnetic field at a point? What is the magnetic field at a point 20 centimeter away from the center? What is the magnetic field at a point 20 centimeter away from the center on the axis of the coil? On the center, on the axis of the coil. This is a circular coil and a point is situated on the axis at a distance 20 centimeter. Question says 20 centimeter. So this time we will be applying the formula of magnetic field at the axial position or the axial case one. What is that formula? We will put that formula mu naught N I A square by 2x square plus a square power 3 by 2. Now we are putting the value. Mu naught value is 4 pi into 10 to the power minus 7 into number of turns. How many turns are given in the question? 20 turns. I put 20. I is current. Current flowing in the coil is 1 ampere. 1 ampere into A. A is the radius of the coil. Remember, in this formula, A is the radius and x is the distance. If you check the derivation of formula, so there we find A is the radius. Radius is given 10 centimeter. 10 centimeter is 0.1 meter square upon twice bracket. X is the distance is given 20 centimeter, that is 0.2. A value 0.1 square power 3 by 2. Now use calculator. In the power, in calculator you can add, instead of writing 3 by 2, you can add 1.5. The power sign is here, and then place the power sign in calculator, add 1.5 and calculate the answer. The answer will come 1.12. 1.12 into 10 to the minus 5. That is the answer. Now next question will be question number 4. Question number 4 here. Question says, find the magnetic field at the point P. Find the magnetic field. Find the magnetic field at the point P. At the point P, capital P, in the figure shown below. In the figures, there are two figures given. In the figures shown below. In the figures shown below. And the figure is given like this. Figure 1, and there is another figure given over here. Figure 2 is given. Figure 2. There are two figures given, and they are asking to find magnetic field at the point P. They are also find the magnetic field at the point P. Okay. Now we are finding the answer solution. For figure 1 we will do at first, and then we will do for figure 2. One by one we will do. Though the figure looks quite complicated, but the solution is very easy. So I will show how we can do. Over here, if you see, there are three kinds of conductor. One is a straight conductor, one is semicircular conductor, and another one is again straight. We are having three types of conductor. Where is the point P over here? So at the point P, we have to find point P is lying on the same line. Okay, if you extend it, it's going to lie on the same line. So magnetic field due to this current will be 0. magnetic field of a straight conductor exists where at a point outside it, not on the point. Point should not lie on the line. When you extend the line, the point must not lie over there. Magnetic field at that point is zero on the same line. Magnetic field is existing only outside around it. So magnetic field at the point P due to this wire is zero, due to this wire also zero, because either you extend forward or backward, the point P lies on the same conductor there. So that means the magnetic field is zero. So we will have magnetic field of only this semicircular coil left over there at that point. So we will be doing directly like this, V equal to, actually there are three of them, 1, 2, 3, but this is 0, this is also 0, only this one is left over. This is semicircle at half of the full circle. If it is a quarter circle at 1/4, half into, what is the formula of full circle? Mu naught n I, n value is 1 only because there is only one coil, so mu naught I by twice the radius. Radius shown out in the figure is A. So that is the answer, finished. Mu naught I by 2 to the 4A. This is the answer for figure A. 1. Now we are doing for figure 2. For figure 2. We are doing it for the figure 2 now. Figure 2 you see at the point P we are finding. So for the point P we are having two kinds of figure. One is this circle and the other one is a quarter circle, quadrant. This one is 3/4 circle, 3/4. This angle is given 90 degree here. In the figure only it is mentioned. That means this figure is representing how many circles? 3/4. And this one is a quadrant, quarter circle. So we'll be adding them up. So we'll add here B equal to, second case, B equal to 3/4 of the smaller circle, 3/4 of mu naught I by twice the radius. What is the radius of the circle? Radius of the circle is A. Let A plus 1/4 of the big one, 1/4 of mu naught I by twice. What is the radius of the quadrant? Radius of the quadrant is B. Let B. So we can just take common and all and find answer now. What is common out here? 1/4 is common. You can add 4 to the 8, 4 to the 8, 1 by 8 is common. Mu naught I is also common. We are left with 3 by A plus 1 by B. 1 by B. This is the answer for this question. Though the diagram looks complicated, but the solution is simple. We see what is a straight conductor. For this point P is lying on the same conductor, answer is 0. Here also it is 0. Only semicircular is left over side. Just use the formula of magnetic field of a semicircular coil at the center. So this is the value. And then this is a combination of two figures. For each figure we are using the formula and adding them up. Adding them up. So that is the answer. Okay, now next question. Now the question says a power line carries a current of 100 ampere. A power line carries a current of 100 ampere in a south to north direction. In a south to north direction. What is the magnetic field at a point? What is the magnetic field at a point 1 meter below the wire? What is the magnetic field at a point 1 meter below the wire? Okay. Question says there is a power line in which a current of 100 ampere is flowing. South north direction like this. 100 ampere current flowing. We have to find magnetic field at a point 1 meter below the wire. 1 meter below the wire there is a point below. 1 meter. This distance is 1 meter. 1 meter below. Here we have to find the magnetic field of this current. What type of current wire is this? Straight wire. So we will apply the formula of straight wire. What is the formula? B equal to mu naught I by 2 pi a. Straight conductor time we have the formula divided by pi. As circular time we have only 2r. Mu naught value I put 4 pi into 10 to the power minus 7. I is current 100 ampere. 2 pi and the value of A is 1 meter. Now calculate the answer will come 2 into 10 to the power minus 5. 2 into 10 to the power minus 5 Tesla. Now we will check the direction. We will check the direction also. Question says what is the magnetic field, and they are talking about south north is mentioned. Whenever direction is mentioned, south north east west, this kind of direction is mentioned, then there we must write down the answer along with the direction. That is why they have given this question. Let us check what direction does it come. You can imagine this way. This is south, this is north. Which side will be east west? Suppose I am having this is the mapping we follow. West, east, north, south. If you turn over like this, so this side is south, this side is north, then this wall will be west and this will be east. You can imagine here is a conductor having current flowing like this way. We are using that right hand thumb rule to find the direction of magnetic field. Thumb you have to keep in the direction of flow of current like this. What direction your finger is closing, the direction the finger is closing is, it can be clockwise either or it can be anti-clockwise. I am sure that the finger is closing in clockwise direction like this. Clockwise. Point is below. So circle is going to come clockwise. So here at that point we must draw a tangent. If you draw a tangent at that point, this circle is going to tangent. If you draw a tangent, will come like this in the direction of west. So here we will write the answer due west, towards west. If you remember in class 10 we had a rule, and on that rule there was a question in Isc Xii batch. The rule was snow rule, SNOW, snow rule. And according to snow rule, when the current flows in the direction from south to the north and a magnetic compass situated below the wire, in what direction the deflection in the compass will take place? Towards west. SNOW. SN means south north and O is just to make a word, and W means towards west, and that is working out to be west. South north and deflection is towards west. If the point is situated, I mean the compass needle or the point is situated below the wire, and that we are working on using right hand thumb rule only. If the point is situated above, so the circle is coming like this above, then if you draw tangent, the tangent will come like this. This way it will come. So this direction will be then east in that case. So accordingly we work out using the right hand thumb. The direction we are giving to west direction. Okay, today we are doing till here. Then next day there are some more types of problem. Then most probably this chapter will be over next day. Okay, we have to do the problems on solenoid, and we have to do the problems between two parallel wires, three parallel wires, and all those kind of problems are still left. We will be doing them in the next class. Thank you for the day.